So let's go ahead and look at an example of a proof by induction using our second definition. So you might notice up here that I have changed our definition to be the second one, when instead of just talking about the natural numbers, you're talking about some other set. And it gives that procedure. So we can see that this particular example actually falls underneath this case, because we are being asked to prove for every natural number n greater than or equal to 5 that this inequality is true. So this part, that's the set we're talking about. And notice that's not all the natural numbers. It's only some of them. Five, 6, 7, etc., etc. And if you watch the previous videos, you can see that yes, indeed, this thing is countably infinite, because I can give the first one a label of 1, I can give the second one a label of 2, etc., etc. So I can indeed apply this proof by induction definition. So that's the set that we're looking at, and then this here is going to be our propositional function. That's our P of n. So let's go ahead and see if we can prove this. So to do this proof, let's follow this procedure. The base case is we have to show that P of our very first element is true. So for our base case, in this particular one, we want to show that P of, and then the very first element of the set that we're talking about. And the set that we're talking about here, the very first element is going to be 5. So we want to show that this thing is true. Well, what is this actually saying? P of 5. Well, that was my propositional function, so I need to plug in 5 wherever I see an n. So this thing is logically equivalent to the claim that 2 to the 5 is greater than 5 squared. And if we do our calculations, or you check it on a calculator real quick, you can see that this is the claim that 32 is greater than 25. And last I checked, yes indeed, 32 is greater than 25, so this is a true statement. So following our procedure, we have established our base case. We have shown that for the very first element of this set, that statement is true. So the next thing that we need to do is look at the induction step. So our induction step right over here says that we want to show that P of sk implies P of sk plus 1. And we're actually quite lucky in this particular situation, because sk and sk plus 1, so that is the kth element of this set, and the k plus first element of this set are actually successive numbers, right? This goes 5, then 6, then 7, then 8, etc. So they're successive numbers. So we have that the kth element of this set is some number, t, and the k plus first element of this set is t plus 1. So it's the next one for some t. So what we're really trying to show in our induction step here is P of t implies P of t plus 1 for arbitrary t. And the reason why I can claim this is because these are successive elements here, and that's what saved us. So we are back into our basic proof by induction step. So what exactly are we trying to show here? So I need to show that P of t implies P of t plus 1. So let's go back to what this claim is. So what we really want to show is that 2 to the t greater than t squared, that being true implies 2 to the t plus 1 is greater than t plus 1 squared. So this is what we actually want to show. So I could just simply write down the proof of this, but what I really want to show you is the actual scratch work and the thinking that goes behind the process of proving a statement like this. So instead of just simply writing down the proof, I'm going to walk through the scratch work about how we would start to build up the proof of this particular statement. And that's what we'll be exploring next.